Hey everybody, Jake here coming at you with another live math lesson this Monday night, 5 o'clock Pacific time. Today we're going to be going over some average velocity problems and kind of how this relates to instantaneous velocity. I got a couple examples for you that we're going to go into, but these should be pretty helpful for you in terms of, first of all, learning the difference between average velocity and instantaneous velocity, and kind of the steps you'd go through to find average velocity. We're going to be going over a few examples, and they each kind of give you a little bit different information, and you have to use that to find average velocity over a handful of different intervals. And so I think this is going to be a helpful video for you because it gives you a couple different kinds of situations where you might be asked to find average velocity using different information. So should be helpful for you. If you do get some value out of this video along the way, do me a favor and hit that like button. It's a huge help to my channel so I can keep making more videos like this, keep getting these videos out to more and more people, and keep growing the Jake's Math Lessons community. As always with these live streams, if you do have any questions along the way, feel free to throw them in the live chat, even if they're off topic. Obviously, if they're on topic, I'd love to hear your questions so I can help address them right away rather than, setting you out and seeing if you can figure it out somewhere else. Rather just help you out and get the question answered right here. So throw them in the live chat, even if they're off topic. I may not be able to answer them right away, but maybe I'll be able to come back and make a video about whatever other questions you have. So can't hurt to ask. But anyway, let's go ahead and jump into the problems here. So here is the first one we have. So we're going to be finding average velocity based on this situation here. We have a bit of a word problem. So we have a rock that's thrown upwards on Mars with a velocity of 10 meters per second. Its height in meters, t seconds later, is given by this equation. So basically, this equation that we're given here tells us the height of the rock t seconds after it's thrown. So we know it has an initial velocity of 10 meters per second. That's basically just kind of baked into the problem here. That's not, a given piece of information we need to really worry about beyond the fact that that's where this 10t comes from. That's the initial velocity. And basically we know that this function is going to accurately model this rock's height t seconds later. So for example, if we wanted to find what the height of the rock was at 1 second, we would be able to just plug in 1 for t, and that would tell us the height of the rock 1 second after it was thrown. So what we're going to have to do in this problem, the problem asks us to find the average velocity over these given intervals. And this is a two-part problem. We'll get into part B in just a second here. But part A says we have these 5 different intervals, and we need to find the average velocity of the rock over these given 5 intervals. So before we jump into that, I just want to take a quick second to explain the difference between average velocity and instantaneous velocity. Average velocity is always going to be talking about well, I mean, I guess it's in the name, but the average velocity or the average speed that an object is moving over a period of time. So that's a very important distinction. Average velocity is going to be referring to the average over a given duration of time. So you can see in this case here, we've been given these 5 different time intervals. We want to find the average velocity from 1 second to 2 seconds. If we were to measure basically where the rock was at 1 second, where it is at 2 seconds, and then find the average velocity between those two measurement points. Same thing here, the average velocity from 1 second to 1.5 seconds. 1 second to 1.1 second. So there's no kind of rule or restriction on how long the intervals have to be. You can see in this case, actually, the intervals are getting smaller and smaller. We have a 1 second interval, a half a second interval, a 0.1 second interval, 0.01 second, 0.001 second. So they can be however short or long you want them to be, but average velocity should always be found over an interval of time. There's always going to be 2 time data points that you want to consider, the beginning and the end of this time interval, and you're trying to average out the speed or the velocity that your object is traveling throughout that time period. Okay. Instantaneous velocity is a bit different. Instantaneous velocity is not going to look at the velocity over a period of time, it's going to look at how fast is something moving at one specific split second. Instantaneous means at this one point in time, how fast is the object moving? So instantaneous velocity, you can see in part B here, it does ask about instantaneous velocity. It's asking what, well, we're going to estimate it using this average velocity, but what it's getting at is for us to figure out what is the instantaneous velocity at t equals 1. So notice the difference. In part A, we're being given 2 time points, 1 second and 2 second, an interval of time, to find the average velocity over, whereas in part B, we're being asked to find the instantaneous velocity at one specific time point. So that's a very important difference between instantaneous velocity and average velocity. Average, you're going to be given 2 input numbers, or 2, in this case, the input is time, so 2 time numbers to look at. And with instantaneous velocity or instantaneous speed, you're going to be given just 1. So there's just going to be 1 input number that you're looking at. What's the speed or velocity at that specific point in time? So key difference there. Now, really when it comes to actually finding these two things, let's go ahead and start in part A here with the average velocity. How you actually find the average velocity is really pretty straightforward, actually. There's just going to be an average velocity formula that you're going to use. So the average velocity formula, if you want to find the average velocity on a given interval, let's just say from A to B, 2 given numbers that you want to find the average velocity over, you're just going to take, you're going to need, first of all, this is if you have a function that models your position. So if you have a position function, position just means where it is at any given point in time. So in this case, it's called a height function. Height is an example of a position function because it's telling us our height above the ground, where our rock is in relation to the ground. So a position function just tells you where something is in relation to a fixed point. In this case, it's the ground. So we can use this height function as position. So if you have a position function, let's just say this function is y equals f of x. To find the average velocity over a to b, all you have to do is take f of b, so basically just plugging in your second point into your function, minus whatever you get out from plugging in your first point into your function, so f of b minus f of a, over b minus a. So you're just going to plug in your second point into your position function, plug in your first point into your position function. That'll be the numerator, is the difference between those two things. And then the denominator is just the difference between your second point minus your first point. So we're just going to use this formula now. And what we're going to do is use this as our position function, y equals 10t minus 1.86t squared. So in this case, we have actually a function f of t instead of f of x. But the way you do it is exactly the same. We have y equals 10t minus 1.86t squared. Okay, so this is our position function, and we're trying to find, we'll start with this first one here, the average velocity from t equals 1 to t equals 2. So we're just going to put a is going to be 1, b is going to be 2. So to find the average velocity from 1 to 2 with this position function, we're just going to first plug in 2. So plugging in 2 into our function, we're going to get 10 times 2 minus 1.86 times 2 squared. Okay. And then what I'm going to do is put this whole thing around parentheses here. So this right here, basically, this whole thing here was just f of b. Okay. Then we're going to do minus in, another set of big parentheses here, f of a. So f of a is just plugging in our first point into our position function. So 10 times 1 minus 1.86 times 1 squared. Whoops. So this is, like I said, this is just f of a. And then on the denominator here, we're going to have b minus a. Whoops. So b is just our second, x value or t value in this case, our second edge of the interval we're trying to find the average velocity over. So that'll just be 2. And then minus a, so minus our first point, 2 minus 1. So it's just going to be our second point minus our first point is our denominator. And like I said, that's just b minus a. Okay. So then you would just have to basically plug this into a calculator. So I'm not going to kind of go through this, solving this step by step. You basically could just plug this into a calculator. I mean, technically you could calculate this all out on your own, but it's kind of long to do that. But in this case, if we were to plug that into a calculator, the average velocity from 1 to 2 would be 4.42. Okay, so the other thing we need to consider is units. Keep in mind that our function outputted meters, and the input was t seconds. So if our output is meters, our input is seconds. That means our velocity is just going to be meters per second. Your units of your velocity is always just going to be the output unit of your original function divided by the input unit of your original function. Okay, so that's going to be this first one. So I'm not going to go through all 5 of these. I'm going to leave them kind of for you to do. But basically the idea is we're just using this formula. We're just plugging in our second endpoint and our first endpoint into the formula for A and B. So in this case, we're going to take the average velocity from 1 to 1.5. We would just use 1 to 1.5 here. And then we're just going to plug in 1.5 for B, 1.5 for B, 1.5 for B. A is still 1, right? Our first point that we were looking at didn't change. That's still 1. And now you would just plug this whole thing into a calculator. And if you do that, you're going to end up with 5.35, again, meters per second. So now that would be our average velocity from 1 to 1.5. So same thing, you can kind of do the same exact thing for these next 3, and I'll leave that for you to do. I will go ahead and show you the answer so you can confirm that you got it right. I'm just going to jot down the answer for each of these 5 directly beneath the interval up here, because we're going to need to use these 5 answers in part B. So like I said, the first one is 4.42. The second one is 5.35. Once you use that formula for 1 and 1.1, you would get 6.094. This one here is going to be 6.2614. And then this last one here is going to be 6.27814. Okay, so like I said, once you kind of just plug those two numbers, the 2 numbers within each interval into the formula, that will give you these 5 numbers as your answer. So where do we go from here? Well, actually, first of all, before we do that, I do want to point out average velocity is actually something that is covered on my free Calculus 1 study guide. If you want to go check that out, there is a link down in the description below or in the pinned comment or pinned live chat if you're watching this live that goes over. This is on there. There's tons of other formulas that I guarantee you're going to find super helpful as you go through Calculus 1. So go check that out. It is completely free. You just click that link, put in your email. I'll email you the PDF of that study guide right away. You'll have it within seconds. So go check that out if you like it, which I'm sure you will. It should be pretty helpful for you throughout the rest of the term. All right, I'm not seeing any questions so far, so we'll just keep on moving along here. So part B of this question now asks us to use these average velocities to estimate the instantaneous velocity when t equals 1. So how do you do that? Well, let's think about what instantaneous velocity means. Really what you want to think about is instantaneous velocity just comes from the formula for instantaneous rate of change. All that formula is the average or the instantaneous rate of change of a function at a specific point. So let's say we're trying to find the instantaneous rate of change of this function that we are given here, y equals 10t minus 1.86t squared. The instantaneous rate of change, just another formula, which also is on my free Calculus 1 study guide if you want to check that out, link down in the description. The formula for that instantaneous rate of change, if we're trying to find the instantaneous rate of change at a specific point, so at t equals 1, for example, that would just be f prime of 1, basically. It essentially just means the derivative of your function at that x value, or at that t value in this case. It's just going to be given by well, actually, yes. So it'll be the limit as t in this case. T is our input variable. As t approaches whatever number is that we're looking at here, t goes to 1, of f of t minus f of 1 over t minus 1. So this formula right here will give us the instantaneous rate of change of this position function at t equals 1. The limit as t goes to 1 of f of t minus f of 1 all over t minus 1. So what do you notice about this formula right here and the formula that we used in the first part here? F of b minus f of a all over b minus a. These look pretty similar, right? This is the formula for average velocity. This is the formula for instantaneous velocity. They're very similar. And in fact, if we're looking in basically what we found in part A, the first kind of data point that we were looking at, the left edge of each of these intervals is all 1. So basically what that means is in part A, when you found that, your A was always 1. We always had f of b, f of our second interval point, minus f of 1, all over b minus 1. Now that looks extremely similar to what we have here. But the only kind of difference here is, in this case, we're taking the limit as t, the number that we're plugging in here and here, as this approaches 1, what number is this whole thing gonna go toward or approach? Whereas here we were just taking some specific b value, some fixed b value, and plugging it into this formula. Well, what do you notice about the b values that we dealt with in part A? So the b values are now these ones here. 2, 1.5, 1.1, 1.01, 1.001. What do you notice about those b values? They keep just getting closer and closer to 1, right? We started 1 whole unit away from 1. Then we went to only 0.5 away, then only 0.1 away, then 0.01 away, then 0.001 away. Basically, these b values are just getting closer and closer and closer to 1. So basically, whatever these answers are from part A, whatever number those are approaching, should be exactly the same number that this limit is approaching. So whatever number it looks like our part A answers are going closer and closer to should be what this limit is going to, which essentially is the answer for part B. So obviously it's an estimate. We don't have to actually find the limit in this problem. But we can kind of just look at these orange numbers here, the answers for part A, and see what we're getting closer and closer to. So you can see these first ones, you know, from 2 to 1.5, these are pretty far away from 1. These answers aren't that close to what we end up approaching. But you can see as we get to the third, the fourth, the fifth, the change in these answers gets smaller and smaller. And in fact, if we were to even take this a step further, go from 1 to 1.0001, of course, this wasn't part of part A, but I just kind of, if you do this extra, you'll get 6.27981. So you can see basically we went from 6.26, 6.278, 6.279. It's just 6.279, maybe 6.28. It might get up to that eventually, but pretty much your answer is going to be somewhere between 6.279 to 6.2. Whoa, that was sloppy. 6.28, somewhere in there. So I think this would be a pretty reasonable estimate for what our instantaneous velocity is going to be at t equals 1. You don't need to get out to like 6 decimal places. That's a little silly. We're really just trying to estimate. So I'd say if you were to give 6.27 or 6.28, that's probably a pretty good estimate. That's probably as close as you need to get. You're not going to need to get closer than that. So that's how we can use different shrinking intervals of average velocity to estimate instantaneous velocity. So, in general, if you're trying to estimate instantaneous velocity at a specific point, you can just look at the average velocity over smaller and smaller and smaller intervals as you get closer and closer to that point. And that should give you an estimate. Now, keep in mind, it is an estimate. So if we were asked to actually find instantaneous velocity at t equals 1, this probably would not be a sufficient answer because it's not exact. If the problem did say within 3 decimal places and we could confirm that this was within 3 decimal places correct, then yeah, technically it would be right. But, if you were asked to leave it in exact form, rounding to 2 or 3 decimal places is not going to be good enough. But if all we need is an estimate, this is a great way to do that. Now, this can really come in handy in situations where you're given a position function where finding the derivative or finding the exact instantaneous velocity at a certain point is impossible. There are functions that you can't take the derivative of. All you can really do is use a computer to figure that out, which is essentially what we just did here by estimating the instantaneous velocity. That basically just used computer type calculations to estimate the velocity over a smaller and smaller and smaller interval, which kind of simulates finding an instantaneous velocity. So pretty cool, cool trick and interesting kind of problem there. Still not seeing any questions in the live chat, so we'll keep on rolling here. But if you do have any questions along the way, as always, throw them in the live chat. I'll do what I can to answer your questions along the way. But let's go ahead and jump into the next problem here. I got another example for you here of average velocity, another average velocity example. So this example is a little bit different. Like I kind of mentioned at the beginning of the video, there's not going to be the same information given in this example as in the last example. In the last example, we were given a function, a position function. In this example, we are given a table which shows us the position of our cyclist in this case. So we're not throwing a rock. We're looking at how fast or where a cyclist is riding their bike. In this case, we're given a table which tells us how far the cyclist has gone at specific points in time. So you can see we have at 0 seconds, at 1 second, at 2, 3, 4, 5 seconds, exactly how many meters they had ridden up to that point. So, right at the start, 0 seconds measured, they've ridden 0 meters. So that's essentially like our starting point. Then 1 second later, they rode a total of 1.4 meters. 2 seconds into it, which just means 1 second after this one, they rode a total of 5.1 meters. 3 seconds into it, 10.7 meters total. 4 seconds into it, and so on and so on and so on. So what we need to do is find the average velocity over these 4 different intervals of time. So just like the last example, we're going to use the average velocity formula, which again is on my free Calculus 1 study guide. If you want to check that out, there's a link down in the description or the pinned comment below. Just make sure you're checking out the pinned comment and not a link from some scammer in the comments. Just use the pinned one. But that Calculus 1 study guide, it's free. It's available for instant download. Just follow that link and you can get yourself a copy. But that average velocity formula, like I said, average velocity, I'll call that AV, is if we have a function, which in this case we don't, but we can still use this formula, and I'll explain why in just a moment. It would be f of b minus f of a all over b minus a. And this would tell us the average velocity over the interval a to b. So basically the output of whatever we get from plugging in our right endpoint into the function minus whatever we get from plugging in our left interval endpoint into the function all over our right interval endpoint minus our left interval endpoint. So how do you gather this information if you're not given a function, but instead you're given a table like this? Well, think about it like this. Instead of having a position function in this case, like we sometimes do and like we did in the previous example, instead of having a position function, we are just given the output of the position function at certain points. So you can basically think of this table as t and f of t, where f of t is our position function. So these numbers down here give us our position at specific points. Yeah, perfect. Glad you're finding that helpful. Appreciate the comment. So basically, what that means is instead of worrying about plugging in b and a into our function, we can just look at the lower row on our table here, and that would be f of b or f of a, whatever number we're plugging in. So like in this case, if 0 is t, f of t is 0. If t is 1, f of 1 is 1.4. So you can just think of this lower row as f of whatever number is in the upper row here. So what we can do, let's start with this first interval here. If we want to find the average velocity over the interval 1 to 3, we can basically just go down here to our average velocity formula. We're going to look at the interval from 1 to 3. You're going to say b is going to be 3, a is going to be 1. So you're just going to replace these b's and a's with 3's and 1's. Okay. Now, looking at our table, we need to figure out what f of 3 and f of 1 are. Well, f of 3 is just going to be whatever the output of our table is when our input is 3. So when our input is 3, our output is 10.7. So f of 3 is 10.7. And then if we want to find f of 1, that's just going to be our output whenever our input is 1. So our output is 1.4 when our input is 1. So f of 1 is going to be 1.4. Okay, so now we can just calculate this out. There's no more like figuring out pieces now at this point. We can just minus this and divide it and see what we get. So doing that, we're just going to get 10.7 minus 1.4, which would be 9.3 over 3 minus 1 is 2. 9.3 divided by 2 would be 4.65, I think. Might want to confirm that with a calculator, but I think that's right. And that would be our average velocity over the interval of 1 to 3. So the other thing that you want to keep in mind is your units. So the units for average velocity is always just going to be the output of whatever your original function was. So our original function had an input of seconds and an output of meters. So the units of our average velocity is going to be the output of our original function divided by the input of our original function. So meters divided by seconds. So meters per second. Let me actually just confirm that real quick. Just want to make sure I did that mental math right. Pretty sure I did, but hate to give you the wrong answer. 4.65. Okay, perfect. Yeah, so that's going to be our average velocity from 1 to 3. Okay, so then we can do the same thing for these other ones. So now we're going to look at the interval from 2 to 3. We're going to need to figure out the output at 2 and the output at 3. So again, we're just going to go f of 3 minus f of 2, so 10.7 over 5.1. Whoops. 10.7 minus 5.1 over b minus a, 3 minus 2. So over 3 minus 2. Okay? And this is going to be from 2 to 3. So doing that, what would that give us? Let me just calculate that real quick. Well, I guess it's really not that complicated because it's going to be 3 minus 2 on the denominator is 1. So 10.7 minus 5.1 gives us 5.6 meters per second. Okay. So then we can do the same thing again for the interval from 3 to 5. So we just need to find f of 5. So we're going to use 25.8. And then f of 3, 10.7 again. So doing that is going to give us 25.8 minus 10.7 over 5 minus 3. And again, you can go ahead and plug that into a calculator. I think you probably are kind of getting the idea here. Yeah, I see your comment. This is a great formula. Yeah, thank you. Should be helpful for you. Definitely want to keep this one in mind as you're doing these average velocity problems. All right, so 25.8 minus 10.7, and then divide that by 2 because 5 minus 3 on the denominator is going to be 2. Would give us 7.55 meters per second, and that is for the interval of 3 to 5. And then lastly, we're trying to find the the average velocity from 3 to 4. So that's going to use the output at 4, the output at 3. So 17.7 minus 10.7 over 4 minus 3. 17.7 minus 10.7 is 7. 4 minus 3 is 1. So that's going to be 7 meters per second. And that's going to be for 3 to 4. Okay, so we found these 4 different intervals. Okay, so now what we want to do, moving on to part B here, we're going to use a graph of our function s, graph of s, as a function of t to estimate the instantaneous velocity when t equals 3. So basically we're going to now use a graph of the function that is given in this table here to estimate the instantaneous velocity. So let me just make a copy of this here real quick. All right. We're going to use a graph of this function to estimate the instantaneous velocity at t equals 3. So we want to look at when t equals 3. So to do that, all we really need to do is sketch a graph of this function here. So whatever this function is with these 6 points in it. So basically we have the point 0, 0. Let's label our axes here first. T, S, 1, 2, 3, 4, 5. And then let's just say 5, 10, 15, 20, 25. Whoops. Okay. Then the point 1, 1.4. So that's going to be pretty close to the t-axis down here. Then 2, 5.1. It's going to be right about there. And it really just needs to be an estimate, right? We're not going to be able to get any concrete data just by looking at our graph. I should say concrete data of the velocity, the instantaneous velocity of a function, by looking at our position graph, right? That's going to be kind of hard to get exact numbers. We're really just looking for an estimate here. So then 3, 10.7, that's going to be just above 10 here at t equals 3, probably right about there. 4, 17.7, so 4 up to 17.7. It's just about halfway between 15 and 20, probably right about there. And then 5, 25.8, so just above this top line here at t equals 5, probably right about there. Like I said, these aren't perfect. We really just need an estimate here. Now what we can do is basically just connect these points here. We should get something that is probably kind of close to a smooth curve at least. And we don't necessarily know that he kind of keeps going like this, but we can kind of assume that it keeps going in that direction. Really doesn't matter because what we're looking for is the instantaneous velocity at t equals 3. So how do you find instantaneous velocity? By looking at a position function. So keep in mind, we are looking for instantaneous velocity from this graph, but this graph tells us position. So this graph tells us how far this person has ridden at these different time points, but we're trying to use it to find velocity. We're trying to find velocity from position. How are those things related? Well, velocity is just the rate of change of position. It's just the slope of position. So if we have a graph of position here, the instantaneous velocity at t equals 3 is right here, is just the slope of the function at that point. More specifically, what we want is the slope of the tangent line of the function at that point. I don't think I have a tool here for making a perfectly straight line, so I'll just do my best to sketch a straight line here. But basically, we want to imagine a tangent line to this function at t equals 3. So tangent line, that's not a very straight line. Probably would be something like that. It's also not great. I think you kind of get what I'm going for here, though. Tangent line should be just a straight line that is tangent to our curve at that point, which basically just means it shares this point. So it's going to go right through this point, 3, 10.7, and it's going to have the exact same slope as our position function at that point. We're just trying to estimate here. We're just taking a bit of a guess. Essentially, we're just trying to figure out the slope of this tangent line. If we kind of look at the slope of this tangent line, it goes up a little bit fewer than 5 units probably. For each 1 unit it goes over. So the slope is probably a little bit less than 5, maybe like 4.5, something like that. Maybe. I mean, like I said, we're really just trying to estimate based on our graph. We can probably go with 4.5. That's a good enough answer. But what we should also find is that basically our average velocities here, as we look at these intervals that kind of close in on 3, should give us something closer and closer to whatever this, instantaneous velocity is at this point. Maybe it is actually closer to 5. That probably is a pretty good estimate. Probably is pretty close to 5 meters per second. So maybe we could go with that. Somewhere in there, we could get it like we did kind of in the previous example. We could get a better estimate of our instantaneous velocity by finding shrinking intervals of average velocity around 3. Based on the fact that our average velocity from 2 to 3 is 5.6, and then our average velocity from 3 to 4 is 7, I'm guessing our instantaneous velocity is probably somewhere between 5.6 and 7. It's kind of hard to tell based on the graph, so maybe 6 meters per second would be a better estimate. You definitely could get a better estimate by following the same kind of process that we did in the prior example, but that should work just fine. So we'll just go with that. All right, I'm not seeing any other questions in the live chat. I do see a few comments. I appreciate the feedback and the comments there. If you did get some value out of this video, do me a favor and hit that like button down below. Subscribe to my channel too and hit that bell icon. I'm guessing you're probably at the beginning of a calculus term right now based on, summer's coming to an end, fall term is probably starting for you. hit that subscribe button. We can keep crushing it all term long in calculus. I do these live streams every Monday night at 5 o'clock Pacific time. So be sure to come back and you can get your questions answered live, go over whatever topics you guys need. I'm up for feedback. So if you have some video ideas, just throw them in the comments, and I'll do what I can to work those in somehow. But thanks for joining. Hopefully I'll see you next week, and good luck on your studies in the next week. See you then.